Buffers is going to be the topic of this lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do DAT, MCAT, and OAT prep as well. I'll leave a link in the description for where you can find those courses. Now, this lesson is part of my new general chemistry playlist. I'm releasing several lessons a week through the rest of this school year. So if you want to be notified every time I post one, subscribe to the channel, click the bell notification. So we've got to start by just answering a simple question. What is a buffer? Well, simply put, a buffer is just a solution that resists changes in pH. And a couple important reasons you want to know why these even exist and why this is a big deal. And one is that a lot of chemical reactions are pH sensitive. They only occur under a certain narrow range of pH, or at least only maybe occur favorably under a narrow pH range. And so often those are going to be carried out in some sort of buffered environment. But more importantly to specifically you and me, is most living organisms only live in cells and stuff like this over a very narrow pH range. So your blood, for example, has a pH of right around 7.4, just on the basic side of neutral. And if that pH goes below 7.1 or above 7.8 for any significant period of time, it's probably because you're dead. So really important that it stays really, really close to 7.4 most of the time. So your blood is definitely buffered against pH changes. So that's what a buffer does. It just maintains the pH of a solution. It keeps it from changing one way or the other. Now, how does it do this? Well, that's based on what it's composed of. And you got to know that a buffer is composed of a weak acid with its conjugate base, or a weak base with its conjugate acid, same diff. But it has to be weak acid conjugate base, not strong acid conjugate base, or weak base conjugate acid, not strong base conjugate acid. So for instance here, so real common weak acid here we have is HF. So and in this case, you'd have to mix HF with its conjugate base, F minus. So if you want to go the other way and mix a weak base with its conjugate acid, we could take ammonia, a weak base, and mix it with its conjugate acid, the ammonium ion. Now, when you add ions, and notice fluoride here's an ion and ammonium here's an ion, those are typically going to be added as part of a salt, like we studied about at the end of chapter 16. So in this case, when you want to incorporate one of these in a salt, because that's probably how it's going to be added, you don't just have a flask or a beaker or a bottle of F minus sitting on the shelf. It's typically going to be some sort of F minus salt, some sort of fluoride salt like sodium fluoride or potassium fluoride. And so it turns out the fluoride salts you want to use, you want the cation to not impact the solution whatsoever. So you want to use what we called in the last lesson in chapter 16 a negligible cation, but you also want to pick one where the fluoride salts are soluble. And so it turns out all the group 1 metal salts in general are pretty soluble, whereas group 2 metal fluorides tend to not be so soluble. So we're going to rule out the group 2s, even though they tend to be negligible. They're not the most soluble with fluoride, for a lot of different compounds, but the group 1s always are, and they're negligible. And so for anions, you're almost always going to have some sort of group 1 metal salt, and sodium salts are the most common by far. So instead of simply writing F minus here, I'm going to write sodium fluoride, and so our buffer would be made from a combination of HF with either like lithium fluoride, sodium fluoride, potassium fluoride, rubidium fluoride, or cesium fluoride, and again, sodium fluoride by far the most common. Now, on the other hand here, with ammonia being the neutral species, now the weak base, the conjugate acid is a cation. And so if I want to mix this with an anion that's not going to affect the solution, I want to pick one of those negligible anions we learned about in the last lesson in chapter 16, which is typically the conjugate base of one of those strong acids. And by far the most common is chloride. HCl being a strong acid, chloride is a negligible conjugate base. And so most common way to get ammonium in there is ammonium chloride. But technically, we could put ammonium chloride, bromide, iodide, ammonium chlorate, ammonium nitrate. Any one of those would work out fairly well in this case. But ammonium chloride, probably the most common one you're going to see. Cool. And again, mixing ammonia and ammonium chloride in the right ratio is going to get you a buffer. And so again, a buffer resists changes in pH, and it's a combination of a weak acid with conjugate base, and oftentimes we'll say weak acid with the salt of its conjugate base, or weak base with the salt of its conjugate acid. And it turns out you need to mix these in similar amounts. So equimolar, or close to equimolar amounts, equal moles. So it turns out you want to have as close to a 1-to-1 ratio of weak acid with conjugate base as you can to get what we call the maximum buffering capacity. So it turns out when it's in that 1-to-1 ratio exactly, that's when you get that maximum buffering capacity, the greatest resistance to a change in pH. However, it'll still act as a buffer if you have as much as 10 times more acid than conjugate base or 10 times more conjugate base than acid. And it'll change the pH a little bit, as we'll see with some of the calculations later. But that's kind of the buffer range. If you get more than 10-fold more of either the acid or conjugate base, it kind of no longer acts as a buffer. It will not resist changes in pH so much. And so we're talking about resisting changes in pH. Well, what might cause the pH of a solution to change? Well, typically what we're doing is resisting changes in pH when either a strong acid or base is added. It's the most common mathematical situations we'll look at. But the truth is when any acid or base is added. And we just want to resist those changes in pH. And the idea is I like to think of it as really protecting water. So because, if you've got water sitting around, which is neutral, well, if you add an acid to water, you're going to convert that water into H3O+. And if you add a base to the water and steal an H+ from him, then you'll convert him into OH-. And this is what we want to prevent. Whether I add acid or base, I want to prevent the water from being converted into H3O+ or OH- because that's going to affect directly the pH. Well, that's why we want to have a weak acid conjugate base combination in there. So if I add a base, instead of water losing the H+, well, HF's a better acid than water. He's more likely to be acting as the acid instead and be the proton donor. And if I add some sort of acid into water, instead of water acting like the base and getting protonated to become hydronium, well, F- is a better base than water, and so F- is more likely to get protonated. And so what you end up having is you're kind of protecting water from getting protonated, we say, or deprotonated, from acting as either a base or an acid by simply having something that's a better acid and something that's a better base in your solution. And what you'll find out is that instead of directly converting water into either hydronium or hydroxide and affecting that pH in a very direct way, you'll find out that just the ratio of HF and NaF in your solution is what will change, and that'll only result in very small changes in pH instead of much larger ones if that buffer wasn't there. So it turns out that's the deal here. And again, want to focus in on something here. So with buffers, it's much more common to talk about their pKa's than their Ka's for the acid in the buffer. So like here we've got HF has a corresponding Ka. And it turns out it's like 6.8 times 10 to the minus 4. But much more commonly, you're going to be talking about what's known as the pKa. And recall that just P means negative log. And so if you have a pKa, that's just simply equal to the negative log of the Ka value. And so if the Ka for HF is 6.8 times 10 to the negative 4, well, if you take the negative log of 6.8 times 10 to the negative 4, you're going to get 3.17, which here in this table I've rounded up to 3.2. So that's kind of the deal. So you got to know what a pKa is, just the negative log of the Ka. And it turns out with buffers, it's often much more convenient to deal with these pKa's than with these Ka's. But you still might be given a Ka, and if you want the pKa, you better take that negative log. But you might also be provided with pKa's as well. So, and you might see this in a biochemistry context if you're a chemistry major somewhere down the road, and you're probably going to get a lesson on buffers on steroids. You're going to get a little more than what you get probably in this lesson. And I have one of those on chadsprep.com. You can find it there as well. But we're not going to quite go in quite that level of detail. We'll start you off slow here in Gen Chem. But it turns out when you have exactly a 1-to-1 ratio of weak acid and conjugate base, it turns out the pH will equal exactly the pKa value. And we'll see the math on this in a little bit, but that's just a convenient point to remember. So if I said for HF and NaF, if it was a buffer produced to have its maximum buffering capacity, at what pH would that occur? Well, you'd find out that that would occur at exactly a pH of 3.2 when the pH equals the pKa. Well, it turns out when you have either 10 times more acid or 10 times more base, that's going to change the pH by exactly 1 unit. You might recall that that pH scale is logarithmic. Well, it turns out it's going to work out logarithmic in this case as well. And it turns out if you have 10 times more HF, the pH is going to end up being 2.2, 1 unit more acidic. But if you have 10 times more fluoride, NaF in this case, then that's going to actually raise the pH up to 4.2, 1 pH unit more basic than when it was 1-to-1. And that's kind of how it works. It turns out, when you've got this ratio of you can kind of look at it as powers of 10, and that's going to move the needle on pH, one pH unit at a time. So if you kind of take a look at this a little differently, if we have 10 times more of the conjugate base, your pH goes up by 1. And again, with HF and NAF, that means going up to 4.2 instead. But if you had 100 times more NAF than HF, that would move the pH up by 2 units, as we'll see, up to 5.2. Now, that wouldn't be a buffer solution anymore, but we would still calculate the pH in the same way. And we'll see why this kind of works out this way. But I just kind of wanted to lay the groundwork for those powers of 10 and how that affects pH before we kind of take a mathematical look at it. All right, so it turns out with that tenfold difference between your acid and base being kind of the boundaries of where it'll function as a buffer, well, that means that your buffer range is going to be right around your pKa plus or minus 1. And so for HF, when combined with its conjugate base, F minus, the buffer range is going to be from 2.2 up to 4.2. That's where anywhere in that range, it'll resist changes in pH, best at 3.2, but anywhere in that range. But you get outside that range, either too low or too high, and all of a sudden it's not going to function as a buffer anymore. And if you add strong acid or base, the pH will probably change more than you want it to. All right, this is acetic acid right here, and acetic acid has a pKa of 4.8. And so if you mix acetic acid with its conjugate base, like sodium acetate, as we'll see in a problem here in a little bit, again, if you mix them in a 1-to-1 ratio, the pH will be exactly 4.8. If you have 10 times more acetic acid, pH would be down at 3.8. If you have 10 times more sodium acetate, for example, then the pH would be up at 5.8. And the buffer range would be equal to 4.8 plus or minus 1. Now, what happens if you got one of these polyprotic acids? Well, with polyprotic acids, they're going to have more than one Ka, and therefore more than one pKa, and therefore more than one buffer range as well. Let's take a look at carbonic acid here a little more closely. All right, carbonic acid here is diprotic, so in this case has 2 acidic protons to donate, and the pKa for the first one being donated is 6.4. Whereas the pKa for the second H plus proton being donated is going to be 10.3. You might recall that we said that for a polyprotic acid series, as you donate more and more H plus, in the last chapter we learned that they get more weakly acidic or less acidic as you go along. And so it turns out less acidic would mean a lower Ka value, but it turns out when you take the negative log to get a pKa, a lower Ka is going to end up being a higher pKa. And so as you can see in going from 6.4 to 10.3, that higher pKa indicates a weaker acid. But it turns out this means that we also have 2 buffer ranges. So if we focus on just the first equilibrium, in this first equilibrium, H2CO3 carbonic acid is the acid in this equilibrium. And HCO3 minus bicarbonate is the conjugate base. And if you mix H2CO3 and HCO3 minus in somewhat close to a 1-to-1 ratio, you can make a buffer right around pH 6.4 plus or minus 1, depending on the exact ratio you use. However, we've got a second buffer range to work with as well. If you mix HCO3 minus with CO3 2 minus instead, in this combination around this equilibrium, HCO3 minus would be the conjugate acid, CO3 2 minus would be the conjugate base. And so when you mix this combination, now all of a sudden you can make a buffer of pH 10.3 plus or minus 1. And so with a polyprotic series, these can be handy because now you've got potentially buffers at a couple of different ranges that might be used. If you see phosphoric acid here with 3 acidic protons, there's actually 3 different pKa's. One at 2.1, one at 7.2, and one at 12.4. And so there's 3 different buffer ranges. Now it turns out the one at 7.2 is pretty convenient. Super common to use a phosphate buffer to make buffers right around physiological pH for like different living systems or for cell cultures and things of this sort. So it turns out that carbonic acid, actually, this first equilibrium is pretty convenient as well. And this is one that's happening inside your blood. It turns out that carbonate's not the only one, but it is the major probably buffer component of your blood. And it turns out that the H2CO3 is actually in equilibrium with the carbon dioxide that you're inhaling. I shouldn't say inhaling, but the one you're actually exhaling. But it turns out it's transported through your blood, and this equilibrium is going on with CO2 and combining with water to form carbonic acid, and then this equilibrium's happening at the same time, and that functions to actually buffer your blood and keep it resisting changes in pH so that you can keep on living. All right, so now we kind of have an idea of what a buffer is. We know how to kind of look at what it is composed of, weak acid conjugate base or weak base conjugate acid, same diff, and we know how to predict when is a buffer appropriate for, what pH range? So, and again, that's the pKa plus or minus 1. All right, well, it turns out there's actually 3 different ways to make a buffer, and that's what we want to address next. All right, so these are the 3 different ways to actually prepare a buffer solution. And the idea is that to really have a buffer, it's not about necessarily only what you add, but what you end up with. And the key is what you need to end up with. You need to end up with close to a 1-to-1 ratio of weak acid with conjugate base or weak base conjugate acid, same diff. That's the key. And it's not necessarily what you stick in there, but that's what you need to end up with. Well, the easiest way to end up with that is just to stick that in there. And that's what we did earlier. So with weak acid, conjugate base, if you mix them just straight up, that's what you put in your solution. And close to a 1-to-1 ratio, well, then it's going to be a buffer. And we saw this when we mixed like HF with a fluoride salt like NaF. And again, if we mix these in roughly a 1-to-1 ratio, that indeed would be a buffer. And so that's the easiest way to prepare a buffer and the easiest one for students to see. But it turns out, instead of just weak acid with conjugate base, you can mix a weak acid with any strong base, or you can mix a weak base with any strong acid. But instead of 1-to-1, now you want a 2-to-1 ratio. And the idea is that when you mix a weak acid with a strong base, the strong base is going to neutralize some of that weak acid, converting it into the weak acid's conjugate base. And if when you're done, you end up with a 1-to-1 ratio of weak acid that's left over and conjugate base that you formed, well, then it's a buffer. So for example, if we take a look at, say, mixing HF with your most famous strong base of all time, NaOH, and once again, we're going to do this in roughly now a 2-to-1 ratio. It doesn't have to be exactly 2-to-1, but somewhere in that ballpark. So if you look at what's really going on here, you've got HF being neutralized by the NaOH. So, and you might recall that for a strong base, it dissociates completely. And what that means is it reacts completely with water. So where it acts as the base and water acts as the acid. Well, we have something that's even more acidic than water here, HF. And so if NaOH would react with water completely, dissociate with water completely, well, then it's definitely going to react with something even more acidic completely as well. And so this reaction goes effectively to completion. It's going to produce some water, H with OH, but then sodium and fluoride is your byproduct. And that's the key. You're going to produce some of the salt of the conjugate base we did here as well. And the key is you want this 2-to-1 ratio. And instead of doing exactly 2-to-1, I'm going to do 10-to-5 so you can kind of see what's going on. But if, say we mix these in a 10-to-5 ratio, and again, if this reaction is going to completion, you could treat this as a limiting reagent problem now. And so which one of these is going to run out first? Well, the NaOH would run out first. And so we'd use up all 5 moles of it. But since these react in a 1-to-1 ratio, you're going to use up 5 moles of the HF as well. But when these react, they produce, we don't care about the water, the whole solution's full of water, it's an aqueous solution, but we produce in a 1-to-1 ratio sodium fluoride, and so we'd gain sodium fluoride. Well, we didn't start with any sodium fluoride, but we're going to gain 5 moles. And so all of a sudden, when this neutralization reaction is done, you're going to have 5 moles of HF left over, and you're now going to have formed 5 moles of the conjugate base NaF. And so a 5-to-5 ratio is a 1-to-1 ratio of weak acid conjugate base, which again is fundamentally a buffer. And so that's why there's not just one way to make a buffer. So you can mix that weak acid and conjugate base in a close to, 1-to-1 ratio, but you could take any weak acid and mix it with any strong base, but you only want to neutralize half of it, not all of it. That way, half of it is left over, and the other half has been converted into conjugate base, just like we saw here. So, and it turns out it works exactly the same way if you have a weak base with strong acid. You want 2 parts weak, just like we had up here, and 1 part strong so that you only neutralize half of it. And so in this case, the weak base I'm going to use is now the sodium fluoride. So we get the same system in all cases. And then I can add any strong acid. Well, the most famous strong acid is HCl, and it didn't matter which one I chose. But again, the key is I want to put this in approximately a 2-to-1 ratio, not a 1-to-1 ratio anymore. Cool, that way only half of the sodium fluoride gets neutralized, converted into HF in this case, but half of it is still going to be left behind as NaF. And so I'd have HF and NAF present in roughly a 1-to-1 ratio. So you might get a question on the test that just says, which of the following would produce a buffer? And you got 3 different ways to pull this off. Some of the common detractors, and a detractor is just another fancy word for a wrong answer. Some of the famous wrong answers, so for producing, for answers that would not produce a buffer, would be like taking a strong acid and mixing it with conjugate base. Well, strong acid conjugate base doesn't make a buffer. It's got to be weak acid with conjugate base. So, and again, they could, give this in a 1-to-1 ratio and it still doesn't matter. That is not a buffer. It's just going to be a very, very acidic solution, it turns out. So because this is a strong acid and the conjugate base of a strong acid is a negligible base, and so this is just a really acidic solution, definitely not a buffer. Now, the other way they might approach this is they could give you this situation again, HF and NaOH. But what they might do is they might put molarities on here. So 0.1 molar, 0.1 molar, and all of a sudden now I've mixed a weak acid and a strong base. And that should, in your mind, you should be like, well, that's a possibility. That is one possible way of making a buffer. But I got to have 2 parts weak to 1 part strong. And here it's 1 part weak to 1 part strong. It's a 1-to-1 ratio. And in this case, an equal amount of NaOH would neutralize all of the HF. All the HF is going to get converted into sodium fluoride. There'll be no HF left. Only sodium fluoride will be in your solution. It will not be a buffer. And so this is another wrong answer for buffers. You cannot make a buffer with weak acid strong base in a 1-to-1 ratio. It has to be 2 parts weak to 1 part strong. So just a couple of common incorrect answers I wanted you to be familiar with for making a buffer. Cool. Now that you know how to make a buffer, now how do we calculate the pH of a buffer and associated calculations? Let's take a look. All right, so pH calculations with buffers. This is really the 5th example of a calculation of pH. In the last chapter, we did calculating the pH for a strong acid, or a strong base, or a weak acid, or a weak base. That was 4 different pH calculations we learned how to do. Well, we've got the 5th one in this chapter, and that is the pH of a buffer. And most commonly we use what's called the Henderson-Hasselbalch equation. And this Henderson-Hasselbalch equation is just a more convenient way to do calculations with buffers specifically. So, and it turns out you can only use this equation if you have both weak acid and conjugate base in the solution together. You've added both of them in there. And the reason that you can only use this in that case is because you actually can't do this calculation if you have a 0 there or a 0 there. That's not going to work. So they have to both have some, which means it's not just a weak acid, it's not just a weak conjugate base. You've got to have both in your solution. Now, it turns out you could just use the Ka expression. And it turns out the Henderson-Hasselbalch expression is derived from the Ka expression. So, and you could just use the Ka expression if you want to. And technically, because you don't just have just weak acid, you also have the weak conjugate base. If you wanted to, you could just use the Kb expression. But you'll find that for buffers, it is just really convenient to use this Henderson-Hasselbalch. So if you look at kind of where it comes from, what we're going to ultimately do is take the negative log of both sides of that Ka expression. So we're going to do negative log. You know what? In fact, let's just do the log of both sides. We'll rearrange it. So we'll do the log of the Ka equals the log of the H plus times the A minus all over HA. Well, property of logs, when you've got things multiplied together, you can separate them out into logs that are summed together, that are added together. And when you divide, you could subtract. So we could make this log of H plus log of A minus log of HA. We could do that, but we're actually, our destination is this guy right here. So we're actually not going to split up the A minus and HA, but we will split up the rest. And so we'll make this look like log of Ka equals log of H plus, and then put these two under their own separate log term, because effectively they're just multiplied, that ratio is multiplied by the H plus. And so plus log of A minus over HA. Now we're getting a little bit closer, and what we're going to do is we're going to subtract this term off from both sides so that it shows up as negative log of H plus on this side, and then we'll subtract log of Ka from both sides. It'll disappear from this side, but end up as negative log of Ka on this side, and then again plus log of A minus over HA, and we're effectively there. Negative log of H plus, that's what pH is. Negative log of the Ka, that's what pKa is. And then you're left with plus log of A minus over HA. Now, one caveat, it turns out there's actually 4 different versions of this Henderson-Hasselbalch equation, and that's really annoying. So because if there's 4 different versions, students sometimes confuse them, and sometimes they're different by just the sign, things of this sort. So it turns out, property of logs is that the log of x over y, in fact, let's write this out. Log of x over y and the log of y over x are related to each other. And it just turns out that one is the negative of the other. Well, so some people write the Henderson-Hasselbalch, and instead of writing plus log of A minus over HA, they write minus log of HA over A minus. Well, I'm never going to write it that way. I'm never going to present it that way. I just caveat for you on the other side of the camera here that maybe you're going to see it that way. I only ever present one way to students, and I only ever do my calculations with this one way. It turns out also, just like we said, technically you could use Ka or Kb for buffer calculations. Well, it turns out there's another version of this that says POH equals PKB, not pKa, but POH equals PKB plus log of HA over A minus, or minus log of A minus over HA. 2 versions of that version as well, and I don't use either one of those either. So 4 different versions of this. I'm only ever going to present and use this one to avoid confusion. It is also the most common one you're likely to see presented as well, so I'm not just randomly choosing one. And so some of you will only see this one as well, and that's actually probably the most likely scenario. If you see some of the other versions, my apologies. So it's not my favorite to confuse students that way. However, I just wanted you to be aware that's why there's other versions, but you can work it with any one of the 4. Any buffer calculation will work exactly the same with any one of those 4. I choose to use this one, the most common one, every single time. All right, so let's do some buffer calculations here. All right, so the first buffer calculation we're going to do here. What is the pH of a solution having 0.10 molar CH3COH, that's acetic acid, and 0.080 molar CH3COO-Na. So we've lost that H. This right here is called acetate. It's the conjugate base of acetic acid, but again, it's going to have a negative charge, so we've got to have a salt here, and we use the sodium salt. This is sodium acetate's formula. So weak acid, conjugate base, close to 1-to-1, not exactly, but that's definitely a buffer. So, and then the Ka of the weak acid is provided 1.76 times 10 to the negative 5. So if you were asked to calculate the pH of this solution, first thing you'd want to recognize is that this is a buffer. Now, technically, you could set up an ice table for our weak acid, set up the Ka expression, but it turns out with a buffer, because you have both the weak acid and the conjugate base, the plus and minus x's are going to be insignificant every time, and we just ignore them. Well, the whole point of setting up an ice table is for those plus and minus x's, which if we just ignore them all, well, then why did we set up an ice table? And so for buffers, I never set up an ice table. I just go straight to Henderson-Hasselbalch, knowing that the plus and minus x's will always be insignificant for any buffer solution. And so in this case, we're going to do pH equals pKa, and we could just write in negative log of 1.76 times 10 to the negative 5. So, or you could calculate that ahead of time here, and that's what I'm going to do. So pKa here, negative log of this, it turns out equals 4.75 in my calculator. And so that's what we're going to plug in right here for the pKa, so 4.75 plus log, and in this case, conjugate base over conjugate acid. Well, the conjugate base was the 0.08, and the conjugate acid is 0.1. And now we'll see for just a minute why the math works out the way it does. So it turns out if you had exactly a 1-to-1 ratio right here, well, then this ratio would equal 1. If it, like, say it was 0.08 over 0.08, or 0.1 over 0.1. Well, if that ratio is exactly 1, well, the log of 1 equals 0. And you'd end up with pH equals pKa plus 0, which means just pH equals pKa. And if you recall, at the beginning of this lesson, we said that when your weak acid and conjugate base are present in a 1-to-1 ratio, that's when the pH equals the pKa of the conjugate acid. And so in this case, we're not at that point. We have a little more of the acid than we do of the conjugate base. And since we have a little bit more of the acid, we should know that the solution is going to be a little bit more on the acidic side. So the pH is not going to equal exactly 4.75. It's going to be a little bit lower. And it turns out if this had been 10 times higher, acid concentration than conjugate base, well, then the log of 1 over 10 is -1, and you'd have 4.75 minus 1, and the pH would be 3.75. What if you had 10 times more conjugate base than conjugate acid? Well, if you had 10 times more conjugate base, the log of 10 over 1 is +1, and you'd have pKa plus 1, and we would have got a pH of 5.75, and that's why it works out that the buffer range is pKa plus or minus 1. And so knowing the pKa here is 4.75, we know it's a buffer anywhere from 3.75 up to 5.75, and as long as we're within that 10-to-1 ratio, we'll be in that buffer range. Well, in this case, we're going to figure it out exactly, and we should expect, though, with a little more of the acid than conjugate base, but not more than 10 times more, we're within that buffer range, but we're more on the acidic side, so the pH should be just a little bit lower than 4.75. So in this case, 4.75 plus log parentheses of 0.08 divided by 0.1, close my parentheses, is 4.65. Cool. And that's how you find the pH of a buffer. It's much easier than setting up an ice table or anything like that. If you go straight to Henderson-Hasselbalch, take the negative log of your Ka to get a pKa, and then plus log of the conjugate base over the conjugate acid concentration, it is not so bad. Now, the harder calculation is the next one we're going to ask in conjunction with it. And this students struggle with this one just a little bit more. And the question is, what would be the pH if 5 milliliters of 0.10 molar HCl were added to 100 milliliters of the buffer solution above, this one we just dealt with? So we're going to take 100 milliliters of this buffer, and we're going to add a strong acid. And the idea is that as long as we don't add too much strong acid, well, because it's a buffer, the pH shouldn't change a lot. It should only change a little. And in this case, we're not adding a ton of that HCl solution, just 5 milliliters of 0.1 molar to 100 milliliters of the buffer solution with fairly similar concentration. So it turns out there's a fair amount more buffer than there is HCl. So the pH shouldn't change a lot here. And so we should expect, our pH is starting at 4.65. We should expect it to go down. We're adding a strong acid. But because we're not adding a ton of strong acid, and this is a buffer, we should expect it to only go down a little, not a lot. Now, let's say we were adding sodium hydroxide instead of HCl, well, and then we'd expect the pH to go up a little, but not up a lot. So how do we actually perform this calculation? Well, this again is a little more of a pain in the butt than the last one. So because you've got a neutralization reaction that's happening. So in this case, you're adding HCl. HCl is a strong acid. And what do strong acids neutralize? They neutralize bases, period. Strong bases, weak bases, all bases. That's what strong acids do. They neutralize any base in the solution. Well, the base in your solution in this case is that conjugate base, the CH3COO-. It is what is actually going to get neutralized by the HCl. And when it gets neutralized by that HCl, the HCl donates its H+, and you're going to create some of the conjugate acid, that acetic acid. And then you'll create some chloride, which is a negligible conjugate base, being the conjugate base of a strong acid, won't affect the pH, and we'll ignore it entirely. Now, because this reaction goes to completion, and again, we know it goes to completion because he's a strong acid and dissociates completely. And if he would dissociate in water and react with water completely, then he definitely is going to react with acetate, an even better base than water, completely as well. So this reaction with any strong acid or base is going to go to completion. And when it goes to completion, that's a limiting reagent calculation. For reactions that reach equilibrium, you need molarities, because equilibrium constants are the molarities of the products over the molarities of the bases. But for reactions that go to completion, you don't need concentrations. You need to know how many moles of everything you have. And so in our case, we have 100 milliliters, and the solution is let's write this out, color code it here. We have 100 milliliters, and it's 0.08 molar. So in the sodium salt of the conjugate base, and it's 0.0, whoop, no, one too many zeros there, 0.1 molar in the conjugate acid. And so you might recall that molarity, we'll erase this in a second. Molarity equals the moles over the volume in liters. And if you rearrange that, then moles equals molarity times the volume in liters. And so that's what we're going to use here. We're going to use our volume and our molarities and multiply the molarity times the liters to get the moles, because that's what we need for any kind of limiting reagent type calculation. And so instead of 100 milliliters, we're going to convert this, divide by 1,000, to 0.1 liters. And so in this case, to find the moles of conjugate base here, we're going to multiply 0.1 liters by 0.08 molarity, so molarity times liters. And when you multiply 0.1 liters times 0.08 moles per liter, you get 0.008 moles. And obviously I made the numbers nicer so I wouldn't have to keep referring to my calculator, but this would be a great time to use that calculator. And then same thing for the conjugate acid. Again, we have 0.1 liters of this buffer solution, and it's 0.1 molar in the conjugate acid. So 0.1 liters times 0.1 moles per liter is going to be 0.01 moles. And then we're adding to this solution 5 milliliters of 0.1 molar HCl. Well, 5 milliliters, that's 0.005 liters. And 0.005 liters times 0.1 moles per liter is going to be 0.0005 moles. And this is what we've started with. Now, these are the two reactants, but notice normally we just add two reactants. We don't start with any of the product, but we have the product already in our solution. We already have 0.01 moles of the acetic acid in the solution, so I'm taking that into account. Now, between the two reactants here, which one's going to run out first? Which one's the limiting reagent? Well, they react in a 1-to-1 ratio, so whichever one there is less of is the limiting reagent. That's the one that's going to run out. So we're going to lose 0.0005 here, and since they react in a 1-to-1 ratio, we'll lose 0.005 here, and it's a 1-to-1-to-1 ratio, so we're going to gain 0.0005 moles of this product here as well. And so if you notice here, I'm going to write this a little funny once. We're going to end up with 0.008 minus 0.0005 here, just what you start with minus the change here. So we're not going to have any HCl left, gone, not in our solution anymore. And now we're going to have 0.01 plus 0.005. And now we know the moles of both the conjugate base that's left over and the conjugate acid we formed, and they're not too different. And so because we have a fair amount of both weak acid and conjugate base in the solution, it's still a buffer, and we can still use Henderson-Hasselbalch to solve the pH. How is this going to change? Well, a couple key ways here. So let's go back, change a couple things here. So and the first thing I want to point out here is that molarity is moles over the volume in liters. So keep in mind, in this case, we could have written this as moles of A minus over the volume of the solution in liters, and we could have written this as moles of HA over the volume in liters of solution. Now the moles of A minus and moles of HA, those don't have to be equal. They could be, they might be, they don't have to be, but the volume of the solution is the volume of the solution. And if you wrote it like this, the volume of the solution could just cancel, which means the Henderson-Hasselbalch could also be written as a ratio of moles. So you could actually write it as plus log of the moles of A minus over the moles of HA, because the ratio of the moles and the ratio of the molarities, it's exactly the same ratio in the end. Now the moles and molarities may not be equal, but the ratios are equal. So notice you can't just anywhere willy-nilly substitute moles for molarity. That doesn't work. But as a ratio of molarity over molarity in the same solution, the moles over the moles would be the exact same ratio, and that's why we're able to do this. Cool. And this is a very convenient way to write this when you've got some sort of neutralization reaction going on with either a strong acid or a strong base. And so the way this works, we'll set this up one more time, and we'll do pH equals pKa plus log. And in this case, let's look at this before we add the HCl. Well, before we added the HCl, we figured out that there was 0.008 moles of A minus. So the original molarity was 0.08 molar, but when that 100 milliliters that we saw as 0.1 liters, we figured out was 0.008 moles. Nothing wrong with that. And in the same light, we also figured out that we started with 0.01 moles. And so notice, whether we did this earlier with molarities and we had 0.08 over 0.1, well, now doing it with moles, we have 0.008 over 0.01, and it's the same ratio. And if you work out this calculation and plug in for your pKa, again, that 4.75, you'll get exactly the same answer we got when we used molarities before of 4.65 was the pH. Except what's nice now is instead of doing this all out the way we did, so you can ask yourself a question. To a buffer, you're either going to be adding strong acid or strong base in most cases on a question like this. If you add strong acid like we did here, well, what do acids do? Acids neutralize bases. And if you neutralize your base, which is on top in the numerator, it's going to go down. You're going to have to subtract. But when you neutralize a weak base, it turns into its conjugate acid, which is why this number is going to go up. How much are they going to go down and up by? Well, as long as you haven't added more of the strong acid than the base you start with, it'll go by down in this case and up in this case by exactly how many moles of the strong acid you added. And that's why we're just going to subtract 0.0005 on top and add 0.0005 on bottom. A lot of students will get a question like this and realize that, oh, the base is going to get neutralized. I need to subtract it. But forget that when you neutralize that weak base, it turns into the conjugate acid, and they forget to add it down here. Now, what if instead of having added 0.0005 moles of HCl, we had added 0.0005 moles of NaOH? Well, NaOH would be a strong base. Bases neutralize acids. And so in this case, this would be the number that would have been going down, and you would have subtracted here. But when you neutralize a weak acid, it turns into its conjugate base, and so you have needed to add it on top instead. And so that's kind of the deal. You can really simplify what the pH calculations look like. Set up your Henderson-Hasselbalch, set it up in terms of moles instead of molarities, and then just figure out, did you add strong acid? Well, then you're going to get more acid and you're going to lose some of the base. Or if you added strong base, well, then you're going to get more of the base and add on top and lose some of the acid, subtract on bottom. And that's going to be the difference. But from here, we can perform this calculation. And notice, let's just write it out one more time before we actually do the plugging and chugging. So we got pH equals 4.75 plus log, and in this case, 0.008 minus 0.0005 is 0.0075 on top. And then 0.01, and actually we can do that in our head, plus 0.005 is going to be 0.0105, and we're good to go. All right, so 4.75 plus the log of parentheses 0.0075 divided by 0.0105 end parentheses is going to get me 4.60. And this, you should be able to ask yourself, does this look correct? And it does. If you recall, before we added the HCl, the pH was 4.65. Adding a little bit of strong acid, and the pH barely went down. Just went down to 4.6. And so, yeah, this was a buffer. We expected the pH not to go down a whole lot. So notice what would have happened if you added, this much HCl to 100 milliliters of water? Well, you'd have found that the pH would have actually gone down several pH units to pure water. Whereas with the buffer, it just went from 4.65 to 4.6, no big deal. So cool. And that's pretty much what you need to know about buffer calculations. And again, one more thing again for when you get to biochemistry, they're going to give this to you on steroids because making buffer solutions for biochemistry applications is super important. And they want to make sure you know how to make buffers in the lab and know what to mix and stuff like this. So if you're actually studying this for biochemistry, you need a little more, check out my biochemistry playlist, not on YouTube currently. It might be, if you're watching this a little ways down the road, but currently you can find it on chadsprep.com. I got a lot of free courses embedded there. So if you need a little more than this on how to prepare buffer solutions, it's there. But if you're in Gen Chem, this should suffice for your purposes. Now, if you found this lesson helpful and you want to support the channel, pretty much that thumbs up button is the best thing you can do to help me with that YouTube algorithm. And if you are looking for practice on buffers or anything else related to acid bases and Gen Chem, check out my General Chemistry Master Course. For less than an hour of tutoring, you get a month's access, less than a couple of Frappuccinos, truth be told. And it includes over 1,200 practice questions, study guides, practice final exam rapid reviews, lots and lots of Gen Chem help. Free trials available. I'll leave a link in the description. Happy studying.